Let's dive into Norton's theorem and make you an expert at it. If you saw the Thevenin's video already, some of this introduction will be redundant, so you can skip ahead. Imagine we have a circuit like this, and here we have a bunch of resistors. Now our goal is to figure out the voltage and current flowing through each of these resistors in the same circuit. To do that, you have to reanalyze the circuit every single time you change the resistor. But what if there was an easier way to do this? What if we can represent this whole circuit like this, and without much trouble, you can place your resistor here and keep exchanging them to get the values we want. We call this the Norton equivalent circuit. Notice how each circuit element is parallel to each other. This is our load, and that's simply the circuit element we need to find values for. This is called the Norton resistance, Rn for short, and this is called the Norton current. In very simple terms, this represents all the current sources and voltages in a circuit as a single current source at the place where the load was connected. And this resistor represents all the other resistors on our circuit as a single resistor, excluding our load. Just a side note, the Norton resistance is the exact same as the Thevenin resistance. When we're faced with the circuit, all we need to do is figure out these two values, and then we can plug in any load we want and get the results we need. The way to find these two values depends on the type of circuit you're given. There are three possible scenarios, and I will briefly go over them and then fully cover them through the examples. In the first case, we have just independent sources. In this scenario, all we do is remove our load and create a short circuit between where our load used to be. This short circuit current is the same as the Norton current. Then we remove the short circuit and figure out the resistance between the two terminals. To do this, voltage sources become short circuits and current sources become open circuits. Now it's just a matter of adding up parallel and series resistors to get the equivalent resistance, which we call Rn or Norton resistance. Once again, this is the exact same as the Thevenin resistance Rth. In the second case, we have both dependent and independent sources. In this case, the method to solve a problem is the exact same as Thevenin's theorem, but you will draw a Norton equivalent circuit instead. So we remove the load and we create a short circuit and calculate the short circuit current. Now here, to find the Norton resistance, we can't remove the sources since we have dependent ones. So what we do instead is first calculate the open circuit voltage, VOC. That's the voltage between the terminals where our load used to be. Then we need to use this equation to figure out the equivalent resistance. We divide the open circuit voltage by the short circuit current and we get Rn, which is the same as Rth. In the last case, you have just dependent sources. Again, the method to solve this is the exact same as Thevenin's theorem. Since there is no current flow in the circuit, there isn't a way for us to figure out the VOC or ISC. So what we do is remove the load and then attach a 1 milliampere current source to where our load used to be. Now there's a current flow in the circuit, and we can figure out the VOC. Now the cool thing is, the ISC is actually just 1 milliampere, since that's what we placed between our load terminals. After that, it's just using the same equation as before to get the Rn value. Now let's go through a few examples to really understand how to use Norton's theorem. Let's start with a nice simple example where we need to find I0 using Norton's theorem. So I0 is the current flowing through this 3K ohm resistor. That's our load and we can remove it. Next, we short circuit the two terminals where our load used to be. So in this circuit, this is what that looks like. Now there's a current flowing through this conductor, ISC, and our first goal is to figure that value out. You should use passive convention to assign the direction of the short circuit current. In simple terms, We assume that current flows down, so from a higher potential to a lower potential. If you get a negative value, then you instantly know the direction of current is opposite to your assumption. We will cover that in the next example. Now to find ISC, you can use any method you like, such as superposition, mesh analysis, nodal analysis, etc. I will use mesh analysis. If you need a refresh on mesh analysis, I have a whole video on it, so please take a look at the description. Let's assume some mesh currents. First, an equation for the leftmost loop. We have just the voltage source and the 10k ohm resistor. This allows us to directly solve for I1. It should be noted here that whenever I use k, it represents 1000 and m represents 10 to the negative 3. This makes it easier to write values down rather than writing 1000 ohms or 0.001 amps. Next, we can write a mesh equation for the whole outer loop going clockwise. So we have 12 volts, but we're entering the negative terminal of the voltage source, so we get negative 12 volts, then 10k ohms times mesh current I1, then 6k ohms times mesh current I2, and lastly, 2k ohms times mesh current I3. We already figured out I1, so let's plug that value into our equation. Let's simplify. Now we can divide all the terms by 2k and then isolate for I2. We need one more equation, and we can write one for the independent current source in the middle. Notice that both I2 and I3 will flow through this conductor. I2 will flow in the same direction as our source, while I3 will oppose it. So I2 minus I3 must equal 1 milliamp. Now we can plug in the isolated I2 value from the previous step and then solve for I3. We get negative 0.75 milliamps, and using that value, we can figure out I2. Now, if we look at our ISC current, we assumed it to go down, so in the same direction as I1, while I2 opposes it. So ISC is equal to I1 minus I2. Let's solve, and we get 0.95 milliamps. Now that we have the ISC, the next step is to find the equivalent resistance. So remember, all voltage sources turn into short circuits, and all current sources turn into open circuits. Now we look into the circuit and figure out the resistance between the terminals where our load used to be. These two conductors are useless at this point, so let's remove them to get a better view of our circuit. Now imagine you're standing where our load used to be. If we go up or down, our path splits into two parts. So that means this section of the circuit is parallel to this section. But notice that this section has two resistors in series. So that means the two resistors are in series, and the combination of that is parallel to this 10k ohm resistor. So our Rn is 4.44 kiloohms. Now that we have both ISC and Rn, we can draw our Norton equivalent circuit. Here is a tip that will help you out. Draw your Norton equivalent current source to always point up. I'll explain why, and you don't have to do it this way, but it will make your life easier. Since we used passive convention when it came to drawing the direction of the short circuit current, if we get a positive value, your Norton current will point up. However, if you ever get a negative ISC value, then you can still leave your Norton current pointing up, but you can write the current as a negative value. Don't worry, this will make more sense in the next example. So we have the current source facing up, parallel to our equivalent resistance, and right here we can place our load. Using current division, we can figure out I0. Remember, in current division, we have the resistor that we don't want values for on the top, and the sum of both resistors on the bottom, and we multiply it all by the current source value. And that's our answer. Let's take a look at another problem where we need to find I0 using Norton's theorem. This one is pretty similar to the one we did before, but I want to show what happens if you get a negative ISC value. So here, I0 is the current flowing through the 4k ohm resistor. So that's our load, and we can remove it. Let's create a short circuit between the terminals of where our load used to be and label our ISC. Now, let's figure out what our ISC value is. Let's use superposition to figure it out. so we focus on one source at a time. If you need a refresh, I have a whole video on superposition, so please take a look at that. Let's start with the voltage source. That means our current source becomes an open circuit. Now the key here is to realize that because of our short circuit and the fact that current takes the path of least resistance, the current will go through here instead of any of these resistors. So essentially, we can forget about this part of the circuit. So ISC is just the current in this loop, and we can easily find that using Ohm's law. Current equals the voltage divided by the resistance. It's really important to keep in mind that the positive side of our voltage source is on the left. So the flow of current will be counterclockwise in this loop. But our ISC is drawn opposite to it. That means we get negative 6 milliamps, not positive. Next, we put the current source back and remove the voltage source. Remember, voltage sources turn into short circuits. This time, because of the short circuit, this part of the circuit will be ignored since the current will flow through here. We can see that these two resistors are in series to each other, so let's add them and we get 9 kiloohms. We can use current division to figure out the current flowing in this branch, which is really just the current flowing through this 6K ohm resistor. This time, the current will flow in the same direction as our ISC, so we get a positive value. Now that we figured out what each source contributes to our ISC, all we need to do is add them together to get the full picture. We get negative 3.6 milliamps. So what this really tells us is that the direction we picked for our ISC is actually opposite to our assumption. But that's okay. Let's go and figure out our Rn value. First, we remove all the sources. Then we look from where our load used to be to figure out the total resistance. I'll remove the straggly pieces of wire to make it easier for us to see. These two resistors are in series to each other, and the combination of that is in parallel to this resistor. We get 1.76 kiloohms. Now that we have the current and resistance, let's draw our Norton equivalent circuit. So this is where things differ when you get a negative ISC value. You have two options. You can draw your Norton current source facing up with a negative current value, or you can draw it facing down with a positive current value. They both represent the same thing, and you will get the same answer. It's completely up to you. I will keep it face up and show a negative value. Let's use current division to figure out I0. If you decided to face your current source facing down with a positive value, just be careful when using current division since the current division equations are set up with the current source to be upwards. So be mindful of your positive and negative signs. We get negative 1.1 milliamps, and that's our answer. Let's take a look at this question where we need to find I0 using Norton's theorem. I0 is the current flowing through this 4K ohm resistor, so let's remove it. Let's create a short circuit between the terminals of where our load used to be and label our ISC. Now how do we find ISC? One way is to use superposition to figure it out. First, we will focus on just the voltage source. So our current sources will turn into open circuits. To better visualize our circuit, I will get rid of the straggly pieces of wires. Now looking at this circuit, we see that because of our short circuit here, the current will take the path of least resistance and ignore both this resistor and this one. In other words, the loop the current will take would be this. So what is the current in this loop? We can use Ohm's law to figure it out. I equals V over R, so we get 8 milliamps. Let's put the circuit back. Now let's focus on a single current source and remove the other sources. Remember, voltage sources turn into short circuits. I'll remove the straggly bit of wire here. As before, due to the short circuit, the current will flow through the path of least resistance. That would be through this loop, ignoring all of the resistors. The only thing we need to keep in mind is the direction of this current source. We can see that the flow of current will oppose ISC, so it'll be negative 2 milliamps. Let's put the circuit back. Now we can focus on the last current source and remove the other sources. I'll remove the straggly wires. Notice again that due to our short circuit, the current will only flow in this loop. This time, the current flows in the same direction as ISC, so it'll be 2 milliamps. The total ISC value is then the addition of all the values we found. We get 8 milliamps. The next step is to figure out our Rn. So let's remove all of our sources and let's remove the extra wires as well. Looking into the circuit, we can see that these two resistors are parallel to each other, and the combination of that is again parallel to the 2k ohm resistor. We get an Rn of 1 kilo ohm. Now we can draw our Norton equivalent circuit. We have our current source, and then our Norton equivalent resistance, and lastly the load we can place here. Now we can figure out I0 using current division. We get 1.6 milliamps, and that's our answer. Let's take a look at an example with independent and dependent sources. When we have dependent sources, the process to solve a problem is exactly the same as with Thevenin's theorem, except at the very end where we draw a Norton equivalent circuit instead of a Thevenin equivalent circuit. So if you want even more examples solved, watch the Thevenin's video as well. In this problem, we need to find I0. That's the current flowing through the 2k ohm resistor. So that's our load, let's remove it. When we do that, our circuit changed. So let's relabel our dependent source voltage as Vx1. To solve this problem, we need the open circuit voltage between the terminals of our load, and we also need to find the short circuit current. Let's start with the open circuit voltage, VOC. To figure it out, we can write a KVL for this loop, but we can't get an answer since we don't have Vx1 or the voltage in this resistor. So the first goal is to figure out those two values. We can use mesh analysis to do that. Notice that since we have an open circuit here, there is no current flow in this mesh. So the only current flow would be in this mesh and this one. Let's start with the left mesh. So we have negative 4 volts, then 1k ohms times I1, then the dependent voltage source, and lastly 1k ohms multiplied by I1 plus I2. Now let's think about Vx1. Notice that it's the voltage of this 1k ohm resistor. And what is the voltage of this resistor in terms of our mesh currents? Well, it's 1k ohms multiplied by I1 plus I2. Why is it I1 plus I2? Notice that the positive sign for Vx1 is on the top. So I1 and I2 are both entering the positive terminal in the same direction. Let's replace Vx1 with our new equation. Now we can simplify. Next, we can write an equation for the right loop. We can simplify this equation as well. Notice that if we multiply this equation by -1 and then add it to our other equation, it eliminates I2. Then we can directly solve for I1. Now that we have I1, we can use that to get I2 by plugging this value into any other equations we have. We get 4/9 milliamps. The next step is to use these values to get Vx1 and the voltage of this resistor. So let's plug in our values to get Vx1. Next, the voltage in the 1k ohm resistor. So using Ohm's law, we get 1k ohms multiplied by I2, giving us 4/9 volts. Now we can finally write a clockwise KVL for this loop to get our VOC. We get 1.77 volts, and that's our open circuit voltage. Now we move on to find the short circuit current. So let's draw a short circuit through the terminals. When we do that, our circuit changed, so we will relabel our dependent source as Vx2. Since we had the positive side of VOC on the left, I'm going to point the current flowing from left to right. Remember, current flows from the higher potential to the lower potential, so we assume it to flow from the positive side to the negative side. To solve for the short circuit current, we can once again use mesh analysis. This time, I will pick all currents to be clockwise. Let's start with the left loop. As before, we can write Vx2 in terms of our mesh currents. Now we can plug this value back and simplify the equation. Next, an equation for the right loop. Keep in mind, we have I3 to worry about in this scenario, since there is current flowing in this mesh. Let's simplify. Lastly, an equation for the middle loop. As before, we can replace Vx2 with our mesh current values. Now we can simplify. We can now solve the three equations to get I1, I2, and I3 using substitution, elimination, or Gauss-Jordan elimination. To see how they were solved, please check the description. The mesh current we're interested in is I3 since that's the same as ISC. It's the same current flowing in the branch. So that means our ISC is 2.29 milliamps. Now that we have both VOC and ISC, we can use them to figure out the Norton resistance. So Rn is equal to VOC divided by the ISC. We can finally draw our Norton equivalent circuit. We have the current source, parallel to that we have our Rn, and parallel to that we can place our load. To find I0, we can use current division. We get 0.64 milliamps, and that's our answer. Let's do an example where we have just a dependent source and we need to find the Norton equivalent circuit between terminals A and B. When you have only dependent sources, we can't figure out VOC or ISC since there is no current flow in the circuit. So instead, what we do is place a 1 milliampere current source between terminals A and B. Now we need to find the VOC between points A and B, which is really just the voltage in this 1K ohm resistor. Let's use mesh analysis to figure it out. We can easily see that I3 has to equal 1 milliamp since the branch current is constrained by the 1 milliampere current source. We can also write an equation for the current flowing in this conductor. Notice that while I1 goes in the same direction as our dependent current source, I2 is opposing it. So we can write I1 minus I2 is equal to Vx over 1000. Well, what is Vx in terms of our mesh currents? It's the voltage in this 1K ohm resistor, and we see that it's equal to 1K ohms multiplied by I1. Let's plug that into our equation. 1K divided by 1000 is just 1, so let's simplify this equation further. We get I2 is equal to 0 milliamps. We can stop here because that's all we need to solve this problem, but let's figure out I1 for the fun of it by writing a loop equation for this loop, and we will go counterclockwise. Let's plug in both I2 and I3 values we found earlier. We can now solve for I1. We get 0.5 milliamps. Anyways, now that we know I2 is 0, then the voltage in this resistor is just 1K ohms multiplied by I3, which gives us 1 volt. That's the voltage between terminals A and B. The great thing is, we already have ISC. It's 1 milliamp since that's the current flowing between terminals A and B. So we can figure out Rn by dividing the voltage we found by our current source value. That gives us an Rn of 1 kilo ohm. So now we can draw our circuit. Yep, that really is what it looks like. There is no current source since our original circuit had no independent sources. So this really is our answer. That should cover the types of problems you will face when it comes to Norton's theorem. Thanks for watching and best of luck with your studies.